Okay, here we're doing lesson 4 in this unit. We're talking about properties of linear relations today. So this entire unit has been about relations, and today we're specifically describing what linear relations are like and some of their properties. Okay, so you've probably studied linear relations before in your previous math classes. So some of this might be a little bit of a review for you. If I was teaching this in person, I would have students probably complete this first side by themselves. So you're welcome to do that if you want. If you want to try this first page by yourself and then come back to the video and see if you've got it all correct, then I encourage you to do that. Okay, so let's have a look here. We've got some relationship here that's being represented in a table and in a graph. It's the same relationship. We're talking about pizza here. We have the number of toppings is our independent variable, okay? And the cost of the pizza is the dependent variable, okay? So we can see on the graph, the number of toppings is shown on the x-axis. We always put the independent variable on the x-axis, and then the dependent variable, the cost of the pizza, is shown here on the y-axis. My shading didn't show up that well on the table. There we go. Okay. So question A says, what patterns do you see in the table? And what you'll notice for linear relationships is that the increase is always consistent. So every time you add a topping, the cost goes up by 75 cents. If the pattern is not consistent, then you don't have a linear relation. So as the number of toppings increases by 1, the cost increases by 75 cents. Okay. So the x values are increasing by 1, and then the y values are increasing by 75 cents. Write a rule for the pattern that relates the cost of the pizza to the number of toppings. So essentially here, our starting cost is $10, right? And the pizza with no toppings is $10, and then every time you add a topping, you add 75 cents. So you could even write like a little equation here. So we could say the cost equals $10 plus 0.75 or 75 cents times the number of toppings. Well, we can use n for the number of toppings because I can see we've used n in the graph there. So that can be like a little equation that we write. It's $10 plus 75 cents times the number of toppings. How do the patterns show up in the graph? So as we can see, and later it's important that we can analyze these graphs. I'm just zooming in so we can see a little bit. As we go increase in the y direction by 0.75, we're going to increase in the x direction by 1. So the rise is 0.75, and then the run, we call it the run, is 1. So we're always going up by 0.75 and then to the right by 1. So if I describe the graph, x increases by 1, and then the y increases by 0.75. How can you tell from the table or graph that it represents a linear relation? Okay, that's important. So from the table, we look at the pattern. Actually, I should say the increases or decreases are consistent. Consistent increases. Could be in another table that we look at later on, it could be decreases as well. But as long as that increase or decrease is consistent, then you know you've got a linear relation. And from the graph, what did you notice about the points? Let's have a look at them. They are in a straight line, right? So that's why graphs are useful. Sometimes they give you a different perspective on a pattern, and here we see that they're in straight lines, so immediately we can tell it's a linear relation without even investigating the pattern at all. So that's kind of the advantage of having a graph. Sometimes it gives you a nice visual that we can notice things, different things about a pattern. Okay, so graph points are in a straight line. Okay, great. So that is done. And again, that should have been a little bit of a review. You have done linear relations in the past, but we're just making sure everyone here is on the same page. Okay, now let's look at two tables. I would like you to try this on your own and then just come back and check with me. Which table represents a linear relation? So to figure out if something's linear, we want to look at the increases or the decreases. So here, let's look at the temperature. It's going up by 5. And let's look at the Fahrenheit. So this is going up by 9. Yep, every single one is 9. So this one is linear, consistent increases. Okay, let's look at the current in amps in the next one. Okay, again here, oops, sorry, I circled too much. The pattern in the x values is consistent. Let's see if the pattern in the y values is consistent. So in the x values are all increasing by 5. The x values, so to get from 0 to 75, we're going up by 75, and then we go up by 225, and then we go up by 375, and then we go up by, 525. So those numbers, those increases are not consistent. So this one is not linear. If you were to graph those points, they would not make a straight line. Okay, again, you try this one. Circle all of the relations that you think are linear. So it should be all the straight lines. Okay, not the, this is called a parabola. Or quadratic function, and that is not a straight line. Okay, let's do some more examples. And again, if you want to try these on your own and come back and check, you're welcome to do that. Okay, here we have a water tank on a farm that holds 6,000 liters. Graph A represents the tank being filled at a constant rate, and graph B represents the tank being emptied at a constant rate. Okay, identify the independent and dependent variables. So if you remember, this is back to lesson 2. The independent variable we always see on the x-axis. I'm just going to scroll down a little bit. And here we see that that is time. It's often the case that our independent variable will be time. So I'm going to scroll back up. There we go. So it's going to be time in minutes. Okay. And then the dependent variable is going to be the output, or we'll have it on the y-axis. In this case, it is volume. Okay, that's our dependent variable here. So volume in liters. So when you're writing the independent and dependent variables, you're not writing the actual numbers that are part of the graph. You're just writing the description of what's on those axes. Okay. Determine the rate of change. So this might be a new term, or it might be a term you've heard before. So the rate of change is like how steep the graph is, or how fast, in this case, how fast is the water tank actually filling up. So remember how before we looked at the change in the x values and the change in the y values? Well, the rate of change is just the change in y values divided by the change in x. It's like how fast is y increasing compared to x. Sometimes this is written different ways. Sometimes this is written like this: change in y over change in x. This is a Greek letter, delta, and it means change in. You often see it in science class. Okay, and you could also write it like this: rise over run. So there's different ways to say the same thing. That is how you calculate the rate of change. So let's have a look at this rate of change here for the first graph. So let's look from point to point. So let's just pick this point here. This point here is at 2,000 for y, and then the next point, the graph went up to 3,000 for y. So that increase is from 2,000 to 3,000. It would be going up by 1,000. So here, graph A, you would have your change in y would be positive 1,000, and we have to include units because units are included on this graph, so it would be 1,000 liters. Okay, and then the change in x, so on this graph, this first point is at 40 minutes, and then the second point is at 60 minutes. So from 40 to 60, that's an increase in 20 minutes. So our change in x would be 20 minutes. If I divide those two numbers, 1,000 divided by 20, I get 50. 50 liters per minute. Okay, the units stay the same, liters per minute. So that means every single minute that goes by, 50 liters are being added to the tank. Okay, and notice that rate of change doesn't change depending on which points you pick. I could have picked these 2 points, would have got the same result. This is an increase of 1,000 and this is an increase of 20. It doesn't matter which 2 points you pick. You could even pick points that are far apart from each other. You'll still get the same 50 liters per minute. So you could have picked the first and last point as well. You would have still got the same answer. You would get 6,000 divided by 120, which is still 50 liters per minute. Okay, let's do graph B. So we're going to do change in y divided by change in x. Okay, let's pick these 2 points this time. This point here and this point here. You can pick any 2 points on the graph to do your change. Okay, let's do the change in y. So the first point here is 4,000, and then the second point here is 1. And notice we've gone down. So we call this a negative change. We've gone down by 4,000. Okay, so minus 4,000 liters. Okay, let's look at, oh, sorry, I'm using the wrong color. I'm going to use pink. Here's the point, here's the point. So we've gone down by 4,000 liters, minus 4,000 liters, because the tank is being emptied, right? So the liters are going down. And then let's look at the time. I started at 20 minutes and I went to 60 minutes. So the time has increased by 40 minutes. So it'd be negative 4,000 liters per 40 minutes. If I divide those two numbers, I get 100 liters per minute, and it would be negative. That makes sense because the volume of water is decreasing at a rate of 100 liters per minute. So every minute that passes by, 100 liters leaves the tank. Okay, so rate of change is just a way to describe how fast the graph is going down or up. So if the graph is going down in this direction as you read it from left to right, the rate of change is going to be negative. And if the graph is moving upwards as you read it from left to right, you're going to have a positive rate of change. Okay, that is the end of the lesson.